Good day to you all. Shall we pray? Oh Lord, thank you today. We exalt your name above all things. We say as we start today class, you grant us understanding and we might retain all and remember them to the product that we might be more closer to you and pass our exams with no delay. Thank you for dancing our prayer. For in Jesus' name have I pray. Amen. So like you can see, today's topic is shear force. Today's class is going to be a long class. Okay. So we are considering shear force and bending moments. Like you see, a beam may be defined as a structural member subjected to external loads at right angle to its longitudinal axis. Example, a beam, say, beams are always longitudinal, you can see. So you can say this is point A, point B. Practically speaking, let's say this is a building, or let's say this is a window of a house. You can have the lintel, you see beam here, the beam like that. So bringing it to for class here, you can see this is a beam. So having point A and point B, the end and the beginning and the end. Now this beam like this, if cross section or this beam, some are determinate and some are not determinate. For example, like this, if you take the external force that act along the longitudinal part, like the external force that act along the longitudinal axis and part, if I take a force like this, this is a force, let's say this is a force here, this is a force here. So let's assume force are acting on this. This can be F1, or you can say RA, RB, and RC. R means reaction or force. So these are external forces. If let's say this RD, RE, the one acting longitudinal are these ones. If the external forces act along the longitudinal axis, it is called a column. Acting along the longitudinal axis is called a column. So the longitudinal, if you remember, you have your latitude and you have your longitude. So these guys are the one acting along the longitude. They are column. While we have the ones that act along the structural member. These are the ones that act along the structural member, these two. These ones are, they are subject to both transverse force and they are axial. So these ones are called a beam column. Okay, this RDRA beam column, while these ones are called column. Okay, so we have types of beam. We have beam, and this beam are classified depending on the kind of support down there. So for example, number one, we have the first type of beam we have simply supported beam. So simply supported beam, overhanging beam, cantilever beam, fixed beam, continuous beam, propped cantilever beam. We are going to be studying all of these aside propped cantilever, and we'll be considering some few examples about this. So these first three are determinate beams, while these last three are indeterminate. These are determinate, while these ones are indeterminate. So we'll be considering them examples by examples. Now, when two beams or when two ends of a beam, example like this is a beam. This beam, when the two ends of this beam like this, when the two ends are simply supported like this, let's say they have it's placed on a roller and this is placed on an hinge. This beam is simply supported. That is when the two ends of the beam are simply supported. When they are simply supported, they are simply supported beam. That is when they just have simple supports. It can be a simple support like this. It can be like you just like this. Practically speaking, when you go to a house and you want to build a house, and in the building of your house, you have a house. Let's say this is a house, a diagram of a house. Let's say we have like that. So this is the front elevation, the front view. Let's say you have the front view like so. Here, considering this front view, you have the window, you have the arc. The arc must not be greater than the lintel. You have the door, you shape it. You have other windows like that. So you have another window here. So you have this here. Now this window or this building has beam here. It has beam here. It has beam here. So you can see the usefulness. It has beam on this window, on this door, the lintel. Here it has beam. So these are practical samples. Practical samples. Now considering the simply supported, we've learned that when the beam rather is simply supported. Example, it just has a simple force here and a simple support here rather. This is simply supported beam. Now when you have overhanging beam is, let's say you have very longer support, then you just place a blank here on it. This is overhanging. Cantilever, this is overhanging. Cantilever simply means you hinge a side to the wall. You hinge a side to the wall. Like example, door. Door is the best example. Then you have the beam like this. So when you have the beam like this, this is cantilever. These beams can have force on it. A man can stand here. Another person can stand here. These are just represented by the force. So if I clean this and I put this here, I said R1, R2, or R1, R2, this, and I said this is A, this is B, this is simply supported. So I'm saying cantilever can also be this, and cantilever is when one hinge is fixed. Might not be to the wall, might be hinge, and there are many forces that can hinge on this, so they can stay on this. There are distances that are there. Let's say distance is 18 meter or 15, anything. So I'm just showing an example here. So cantilever here has end and it has end, it has beginning, and the end is infinite and is inside the wall. The end there is inside the wall, into the wall. So in this case here, if I put this on a roller, this is an example of a roller. Diagram of a roller. A roller is like this. It's like a ball. This roller can move. Now this has become simply supported. If one side is hinge and the other is roller, it's simply support. That's this guy has changed to simply support. But if otherwise no roller there, it's just like this. This is a cantilever. We have fixed beam. Fixed beam as well is beams that are really fixed. Example that are hinge, like the building, the window, like I said earlier. So this is a fixed beam. So we have continuous and prop cantilever. So and like that. Now these types of beam each has its usage and each has its effects. Okay. So shear force now. Shear force is example, you have a beam, let's say simply supports, and this beam is long like this, having two ends, let's say point A, point B. So shear force is, it means the tendency for a beam or a beam, the tendency for a beam to be sheared or to be split, or for you to be able to divide it in a simple term. So if I want to shear this guy, I can cut. Imagine I cut this like this. So if I cut this like this, I'm gonna have this view. So that means I'm sharing this now. The word share. So this point cannot be called cross section point. Let me say this point is x and x. Like you're just sectioning it. So A and B. So at each point you have the distance from here, you have the same distance here, but you just need to have this distance as well here, this one as well. That is what shear force is. And also we have types of load. We have point load. We have number one, we have number two, we have UDL, which is uniform distributed load. We have, this is UDL. We have VDL, which is varying distributed load. VDL. Number four, we have combined load as well. We have these ones here, they are concentrated load. These are all concentrated load. And we have combined load. So this we have, you can split them into two generally. The load can be split into two generally, which you can classify them as concentrated load and distributed load. A concentrated load is a load whereby all the force acting on it, that one point. Example, now if I draw a beam like this, you have this guy here. This is a concentrated load. You can see that this load here, let's say 50 Newton, is acting at this point, so it is being concentrated on this point. But unlike, look at the second scenario, let's say we have a beam like this, and I have many force acting on it like this. This is a VDL, a UDL rather, uniform distributing load. So if I change this thing like this, is distributing. This is distributing. That's why it is uniform distributed load. So these are distributed load, but concentrated load is like a point load. Okay, and combined load is when you now have both. Example, on this one, I extend this and I say I have here I have simple supported, and I have this, and let's say there's no other load here again. This is a combined load, and they will all have their distances. They will all have their distance. Okay, so that is about types of load. Okay, now coming to calculation. Also, we have types of support. Before we go to calculation, types of support are ENG. I told you ENG is like this. When you have it like this, it's fixed. It can be like this, it's fixed. So you put beam on it. You can put beam on it. Okay. While roller is the one you have like this. Can also be fixed like this, and but we have it can have in form of a roller form. That will be rolling. It can be single like this. This is a roller, and that is inch. These are all used in beams. Now this is a question. Says that draw the shear force diagram and bending moment diagram of diagram below. Shear force diagram. Okay, solution. This shear force diagram, you can be asked, it can be changed to S.F.D. You can call it S.F.D. shear force diagram, and the bending moment diagram can be B.M.D. as well. Okay, so if you want to solve this kind of question here, you find out that that you need to resolve the component first. Okay, so here, first thing in this diagram is, first you need to know bending moments, or you need to know moments shear force. All right, so this is a typical sample or the solution. So before the solution at all, let me show you something. Let's say this is a diagram here. You have you want to interpret such question. First thing is here you're not told the ruler or you simply support. Okay, it's simple, is simply support. You can have first thing, your here is your A first. Point A, here B. Okay, you can just place it like this, draw a diagram like this. Then the force acting on it is in this diagram here. This is a force 15. So next thing you do, 15 kilonewton. It's important you draw a diagram, know the total distance. This is 1.5 meter. Then you know here, if here is 1 meter, what will be here? Here will be what? 1.5 minus 1, that will be 0.5 meter. Okay, now that is the first stage. First, the next thing you do is you take bending moments, and you take we call something point load. This is a point load. So to continue the solution of this, let me show you something. So take for example this diagram here. In this diagram you have reaction RA, you have reaction RB, force RA, force RB, and you have it hinge at this point. Let's say this point A and point B. Next thing you will do is you first of all calculate the point load. Before calculating the point load, you will list out the parameters you have, don't forget. So let's say this is 50, 70, you list it out. RA is equals to 50 Newton or kilonewton, thereabout. Okay, so next thing you do here, since there's no parameters given here, it is a sample, you write this is a point load. How do you know if it's point load? I told you different kind of loads we have. Okay, so you pay attention. This is a point load, it's just concentrated. Adding it to a UDL, it will be something like, it will be like this. Adding it to a VDL, it will be like this. Then here you now have the beam on top. Here you can have the beam on top. And you have point A, point B, point A, point. Adding is cantilever, I told you already. You have fixed beam. So thereabout. Okay. So in this concept here, we're having a simple word point load, and this point load here, the first thing you do, since this is point load already, you calculate RA clockwise is equal to anticlockwise. Okay, what I say? I said clockwise is equal to what? Anticlockwise. So I'll take this clockwise first thing. So and that is moment. Moment is equal to force times perpendicular distance. Okay, moment is equal to force times multiplied by the perpendicular distance. The arrow indicates the direction of the distance. Okay, so applying it here, we can now say after point load, next thing you do is you take the moment for this. So if you want to take the moment, that will be first thing, the reaction, that is this A and B. So you can simply say this is force F1 and force F2. So let's say this is F1, F2. So you can say this is RA and RB. Okay, they are the support behind it. So you can say RA plus RB. These are force solution. Clockwise is equal to anticlockwise. So this one acting downward is equal, these guys, we tend to act upward, So RA plus RB because of the total force at the other side. That will be RA plus RB is equal to the total force here is F1 plus F2. So let's take, for example, minimize this question. So let's say, for example, here we're having a single force this point here. Let's say F1 or let's say F. So that means RA plus RB equals to what? F. Okay, let me give you an example. Let's say, okay, that we have another one here, let's say this is 2, this is 5 kilonewton. So what will be the answer? That will be RA, reaction support at first end and last end will be equal to RA plus RB equal to F plus 5 plus 2. Note, these are addition. Okay, clockwise is equal to anticlockwise. Now if we have our F as, let me say, let's say our F is acting like this. This direction can also be similar to this diagram. That means we have our RA, we have our RB, We have this F here, we have our 2 here, we have our 5 here. So you will note, or you will see that in this concept here, it won't be like this again. The answer will be, yeah, let's go, that will be clockwise equals anti-clockwise, RA plus RB equal to, there's a mistake here. You know, your F is acting up, so the direction of these guys are acting along the X and Y axis. So this is along the Y positive axis, this is along the X positive axis, and these are the negative parts. So you see, these ones are acting along the positive axis. Okay, so what you will do simply is for this one here, it will be RA plus RB, you know, that is the acting along, and this one too is acting alongside, plus F. Okay, I come again, that will be RA plus RB plus F equal to, so that will be plus 2 plus 5 equals to 2 plus 5. That is RA plus RB plus F, that is in the same direction, equal to 2 plus 5 because they are coming down. Okay, so that is that about that. Now going back to the sample of this, we have this guy. So let's say we have a simple sample like ordinary F, then we can have it as RA plus RB equals to F. Now this you term it as point load. Okay, this is point load, and therefore that is, in this context, the reaction at point A and point B. So this is reaction at point A and point B. The next thing you do is you can make this is it as equation 1, so you can say RA equals to F plus RB, or you can simply say, or you say RB, or rather you say that is F minus RB, like this. That is equation 1. So therefore from this context, or from this concept, you can now take moments. So let's say the distance from here to here is 5, or you say L, let's target L meter. Now taking moments at point, you can prefer taking a moment at point A, semicolon. The next thing you do to take moments here, don't forget to take the moment here, it would be this. We could redraw it. Okay, you're gonna have it as this is diagram like this, A, B. So you have to RA, RB. You have here as F, so you have this length as L, and from this length as L here. So we'll find out that our R, we've gotten RA plus RB equals to F, and from there we can make our RA equals to F minus RB, equation 1. So now taking moments, take moments at point A. So taking moments at point A, semicolon, gives us, in taking moment is your moment, your force times the perpendicular distance. So these are all force, these three guys are force. So if I take moment about point A, all force will be redirected back to point A. I come again. If you are taking moment about point B, every force will go back to point B. They will redirect themselves, or it adds itself back to point B. So if I were to take my moment in point A now, this RB will go like this, and this F will go like this, or simply this RB will go and this F will go. But the direction at which RB is moving is up, so like this, and this man will move like this. Okay, so simply you can see say is moving and is moving. See, all force will direct itself back to the point you are taking the moment. So taking moment at point A means RB force times the perpendicular distance. So next thing to now be RB times the total length it covered. So that is, take moment at point A will now mean RB, that will be RB force times the distance it's covering. RB is covering total length of L to this point. That is RB times L. Okay, and that is what? That is clockwise equal to anticlockwise. So that is clockwise equal to anticlockwise. So this guy is moving and this one is moving. So I have it as RB is covering this total distance to here and F is covering what? Half. If you are not given the specific distance of from here to here, you should divide into 2. Imagine you are given here as L over 3 and here is L over 1 or wherever. That means you are going to multiply your F times L over 3. But in this case, it's L over 2 and L over 2. That is, you divide L divided by 2. That is a half. So that will be RB is covering this distance of L and F is covering half. That will be equals to F times L over 2. Okay, so I can make my I can find my RB here. So I can say that RB will now be equal to FL over 2. That is RBL, FL over 2. And I can now say therefore RB will now be equals to FL over 2L. That is bringing L to this side. L will cancel. I can now say RB equals to F over 2. Very fine. Equation 3. Equation 2 rather. So you can now put RB inside here to get your RA. Okay, and therefore we can have it as RA equals to F minus F over 2. That is simply 1 minus 1 over 2. 1 minus 1 over 2 will give you half. So therefore we can say RA equals to F over 2 kilonewton. Now this answer, you can simply get this answer by simply applying this basic cheat. I call it cheat because it's very basic and it's very simple. Look at this again, and you have point A, you have point B, you have a force acting at center, and this always work for any question like this that is acting at the center. If I say what is your RA, your RA is just divided by 2, F divided by 2. Wow, you see that? That is the answer. Because for any simply supported load that acts the force acting at the center without any other external force aside that, the answer is F over 2. And if you remember, your RB was also F minus F over 2. Okay, that is your RA, your F minus the F over 2 there. So, and that's very simple there. So now let's consider a question before we come here. So consider this question. The force, let's say the force is 5 kilonewton and the distance is 10 meter, and you have it as A and B. You see, draw the shear force bending moment diagram of this question. So first thing you do is what is a point load, right? So point load. So for point load, you have the force acting on it to be what? That is the force acting on it to be 5 kilonewton. So you're gonna redraw a diagram. So solution, you draw a diagram like this. So when you draw a diagram, you change this thing to support like this to force. Okay, that will be RA, RB, and you draw the distance, that is 10 meter, and you draw the force there, that is 5 kilo. So you specify this is what this is 5 meter. If you divide this by 2, okay. So from force, then the L is equals to 10 meter. That is the total load. So therefore, I can now resolve problem by saying first thing RA. You see, these are acting. RA plus RB equals to what? 5 kilonewton. That be total force acting on it. Okay. So next thing I do is this is first. Then you can make your RA subject of formula. That would then be 5 minus RB equal to, and that is equation 2 rather, equation 1 rather. So next thing is you take your moment. This is the reaction taking this is the reaction at point A and point B at both ends. Now you now take moments. So taking moment at point A, you now have, make sure you are actually taking moment at point A. So taking moment at point A, you now have it as here. This force will direct itself back here, while this will come here. So if RA is coming here like this, that is clockwise, right? So in other words, you can come like this and you can just draw like this for simplicity, to not count, not destabilize or disfigure this diagram. So RB and R and this 5. So because I'm taking moment at point A, RB will cover all the total distance RB is covering will be here, and RA with the 5 will come here. At the beginning, I'm taking my moment at point A, point B. RA will come here and 5 will come here. Okay, and don't forget, you must stick to taking your moment at a point to not cause confusion. So better still, you can do it to versatile at both, but for now pick A. Okay, so picking making our point, our moment, taking our moment at point A will now be RB times the total distance, because moment is force times the total distance. So and we have 5 meters here. So therefore this will be RB times what? 10. That is the total distance RB is covering. So that will be 10 RB clockwise equal to anti-clockwise, and 5 is covering how many distance? 5 meters. So that will be 5 times 5, and that in other words that will be 10 RB, that is RB equals to 25 divided by 10, and RB equals to 2.5 kilonewton. So from here you've gotten RB to be equals to 2.5 kilonewton. So therefore you can just come here, substitute RB inside here. That will be RA equals to 5 minus 2.5, and our answer will be 2.5 kilo. So our RA is 2.5, RB is 2. So R is 2.5. So the other cheat method for this kind of question is if you are asked, let's say OBJ question, what is RA? I told you just divide it by what? By 2. So that will be, here initially you can get your answer that RA is equal to 2.5. Then RB will also be 2.5, even without going through this stress. Okay, very fine. And now let's consider this also question as a classwork. Let's say we have our distance here, point A, point B, and we have here as 10 kilonewton. And this 10 kilonewton here, you have so the total distance is 20 meters. So what will be your RA and RB? Don't guess, be appropriate. So RA will be equals to 10 divided by 2, regardless the distance. That will be 5 kilonewton. RB is 5 kilonewton. If you do it to attempt it using the resolution of taking the moment and applying shear force method like I just solved earlier, so and you can contact and subscribe to the channel as well. Do it to subscribe to it so for update, and also click the icon button so that you can do it to the bell button so that you can do it to get is like the script like this, the bell, and it has one bell ringing, so you can do it to click it so that you can do it to get update. And also if you have anyone that wants to join, just tell them to. It's very important you don't just benefit from this alone. You can tell your friends, you can tell your friends, you can tell them, and they should just do it to chat me up, okay? And you can, and you let me be aware first, okay? So that is that about that. Yeah, now to this question, this is you having to be 5 kilonewton, right? So the next thing is to draw the shear force moment. So to draw the shear force diagram, S.F.D diagram, is that you must take the shear force for each point, okay? To draw the shear force diagram, you must take the shear force for each point, okay? And also, so taking the shear force for this, you must take it for each point. So if you want to draw the diagram for this, you find out that you need to draw for, so drawing it again we have the diagram rearranged to now be this. So I'm gonna have it like something like this. So we find out that our RA and RB is 5, 5, and I can redraw this again to now give me something like this. Yeah, so I can have my force here as 10 kilonewton rather, and I can have my RA to be 5 and to be 5 kilonewton. So you can have a distance to be 20 meters. Okay, so now in this concept you can remember your distance here will be 10 meters, 10 meter. Okay, so you must take the moments, the bending moment at each point and the shear force at each point. Here lies the stress. Okay, and it's very simple. So what you do is you find out that at point A, if you are to take the shear force here, the shear force is just, you consider the force. That means if you shear here, if I cut this point away, if I'm cutting this point as initial, my shear force will be equivalent to the force acting on it. Okay, so the shear force is equivalent to the force acting there. So is there any force here? There's no force here. If I draw a diagram like this now, and we said maybe we calculate the force here to be 10, and I say what is the shear force? The shear force at the beginning is equivalent to the force acting on it. Okay, so here the shear force here at point A is equal to 0. But in this case, you can find out that the shear force here, you see, is what? This is acting as 5, okay? But it's not 0. This is equivalent to what? 5. That is 5 that is acting, that is pushing it. If I cut this, okay? So, and now in this concept, you will find out that the shear force here is 5 kilonewton. Now you can write this to be shear force x. Let's take the distance as x at x equal to 0 meter. Okay, so this is just an intonation, you can rearrange it. Okay, sorry, this is just an abbreviation sign, abbreviation, the way you can write it. So this is shear force at x equal to 0. So this is when x equal to 0 meter, and at the shear force here you have it as what? 5. That is plus, don't forget, put your sign, plus 5 kilonewton. It is very important to put the positive sign because sometimes you might have the negative part there as well. So next thing you do is 5 kilonewton. Now at point, when it's shear force when x equal to what? 10. That is that when you get to middle, when x equal to 10 meter, the shear force there will now be this one minus this. You see, you are talking about the force, not about the distance here. So that will be the 5 kilonewton. You know it's positive, right? Plus 5. That will be plus 5 minus, this is acting down, right? So this is plus 5 minus 10. That will give us minus 5 kilonewton. Don't forget, it must come to a balancing. So that will be plus 5 minus 10. That is, I want to take shear force at x equals to 10 meter. That means I'm cutting this at the middle. So I can have a diagram like this. Okay. So if I cut this at the middle, the shear force, that means we are not considering this part. We're only considering this part. And that is that will be the 5 minus 10 here. Okay. Because the 5 is acting up and the 10 is acting downward. Now shear force also at when x is at point B, or let's say at 20 meter, the shear force there is it's very constant when you get here, and it comes back to 5. Okay, that'll be minus 5 plus 5, right? So and that is equal to 0, and that'll be equal to the 5. That'll be equal to 0. Is, you will say minus 5 plus 5, that'll be equal to 0 kilonewton. Now, very careful to make sure that sometimes if you turn to 2 plus 5, it must come back to 0. So you can sometimes you can put it as 5 kilonewton, bearing the fact that the shear force already is equal to the force there. You get what I'm saying? That overrules use doing minus 5 plus 5. Okay. So also it remains constant up to B, and the shear force at that end there is very constant. So the shear force is equivalent to 5 kilonewton. But if you resolve it, that will give you 10. It will always resolve back to 0. That will be minus 5. That is from here. The shear force at this point. So you can also say it to be what? 5 minus 10 plus 5. That will be equal to 0. And the shear force will go back to 0. Or you can simply say plus 5. It will still come back to 0. Okay, that is for shear force. So the shear force diagram now look like this. Yeah, I gotta clean this. Okay. So the shear force diagram of this guy will look like this, because they are simply supported. Here, be very careful to draw a diagram. at this point here, you have the center. You first of all draw this very straight, okay? Draw this as well. The center here, you have the 10 acting, then you depict it there. So we put it there, and as well also, so you need to make sure the diagram is very straight, okay? So you first of all draw the diagram you're given that you should solve the shear force. Now this is the diagram, okay? The load, the point load diagram, and now is now the shear force diagram. But here you can give it some distance because you are going to draw this on a graph, okay? So let's say this is a graph, then you plot on your x-axis. You understand? Now you have a graph like this, the graph sheet. You plot your x-axis, your x-axis, your y-axis. Then you're gonna put your diagram. Just having plotted here, you place your diagram. So most times it's preferred when you draw it at the center. When you draw it at the center here, you do it to make sure, or otherwise you can draw it beside it. If you're not an expert, so you draw it beside it here. You plot your graph, you plot your table x, y axis. Then at this point you count it, let's say 5. Okay, so you put it here, the diagram. So you can draw it up here as well. So we're gonna consider that later soon. Now, but first thing is sketch it first. So this is the load. Now the shear force at point A here. So the shear force at point A here is 5. The shear force at point A is 5, like you see, plus 5. So plus 5 from here, it would, this is a point, this is the initial point, this is initial point, the neutrality. So at this point here, the shear force at 0 is plus 5. So you will count from here is plus 5. So let's say this distance is 5 kilonewton here, plus 5. Now it moves straight, constant, then drops. That is 5 minus 10 will give you minus 5, right? So it will drop. This 10 is dropping. See, it's acting. That means there's a load on it, acting downward, okay? Now this will be plus 5, and when I get here, it's minus what? 5. So this is 0. It drops, and I count minus 5. Minus 5 is here, right? This is plus 5. This is minus 5. So it drops to minus 5. I have something like this. It's constant as well again and drops back to plus 5. Okay, so and that is 0. So here you can say it drops back to 0 kilonewton. That is from here plus 5 constant, it drops to what? Minus 5. So my minus 5 is here, then constant again to 0. So it's constant and goes back to what? 0. This 0 here is obtained from your 5 minus 10. That is minus 5, and minus 5, that is minus 5 kilonewton plus 5, that equals to 0. Or you can simply say plus 5 kilonewton. The plus 5 kilonewton must be speculated at the edge, okay? Now if it's plus 5 kilonewton, when it gets here, this is 0, right? This is minus 5. So minus 5 is plus, the plus 5 will not be this top here. This plus 5 statements indicates that it is minus 5 plus 5 will give you the 0. But if you don't get that, simply do this calculation and you have your 0 kilonewton. So go for the 0 kilonewton to not be confused. I read myself. That is 5 minus 10, that is minus 5, and that be minus 5 kilonewton plus 5 equals to 0. So I have my 0 here, and when I get a plus 5 constant, the 10, this is minus 5, right? At this point, minus 5 here, then constant and what? Get back to 0. So this A, and this B rather, and this A. So we're gonna draw our bending moment diagram as well downward here, okay? That is a later case. So now if it were to be on a graph, you have your graph sheets like this. It's very important. You're gonna have your graphs. That is for X2 chapter as well. Generally, if you are solving question on this, so this is your graph. You plot your table, it's not your table, rather you plot the line there. So having plotted this, you do it to from here, most especially when you plot this on a straight line, you don't need to plot this x-axis. You just plot your y-axis very straight. Then you pick the point load is here. So let's say you pick this point as the beginning of it. Then you pick okay, let's say 5. This is your distance. Just put a measurement here. You want then draw the load. So having drawn this load here like this, you can now section it, so you can get the shear force diagram on a graph. Okay, so for the shear force diagram as well, you can pick a point as well. Then you say, okay, this is 5. I have 5 here, constant. I come down like this. So this is the shear force diagram. The shear force diagram will now look like this. Okay, so that is shear force diagram for this vein. Okay, so and we're going to consider the bending moment. So look at this. Now the bending moment is, you just take the moment. It's not that really hard. Just take the moment. Okay, so if I don't take moment, we've explained that before. Taking moment at point A. So taking moment at point A, that is at this point A, every force will direct itself back to point A. You also do the section. So bending moment when x equals to 0 meter will now be equal to, at the beginning and the end will always be 0. Okay, don't forget that, because the bending moment here, the bending moment is force times distance. The force here times distance. The distance here is 0, right? That will be force. The force here is 5. 5 times 0, that what? 0 meter. So it's just very useless, because the bending moment at every point, the beginning and the end is always 0. Okay, so the bending moment at the beginning here is, the force is 5 and the bending moment is force times distance. The distance is x equals to 0 meter. And next one, the bending moment as well, when x equals to, here you try, make sure you section this very well. If it were to be UDL, I branch. If it were to be UDL, uniform distributing load, like this, like this, like this, like this, the uniform distributed load you need to pick your x, you need to section it very well. Like you take it for two distance, equal distance, 1, 2, 3. But in this case, we can jump to 10. So when x equals to 10 meter, if it is to be UDL or VDL or combined load, you don't jump. Okay, so bending moment at point, when x equals to 10 meter, will be force times distance. So this will not be at point A now. Now the force bending moment when x equals to 10 is here. So the force is acting up, right? The distance is covering is what? Is 10, right? So that is this force. The force is 5. That will be 5 times 10 meter, right? And that will be equals to what? 50. You don't forget your bending moment is in kilonewton meter. That will be 0 kilonewton. And this will be 50 kilonewton meter. Okay, that will be force. The force acting times the total distance is covered, which is 10. Next one, the bending moment when x equals to what? You can take the bending moment when x equals to 5. Okay, let me show you a sample. Let's say bending moment when x equals to 5. It should be on a straight line. It should be very curved and very slant, rather vertical or diagonal. So when x equals to 5, that will also be what? You just like a section it when x equals to 5. Yeah, you are cutting it. Okay, and that will be equals to this 5. When x equals to 5 is, the distance is 5 meter. That was 25 kilonewton meter. So you can also do it for x equals to 20 meter. Don't forget, only for simply support can you jump this. Do not do it section by section. If it were to be UDL, I repeat, you do it single line. You do it line by line. You do the distance to be equal. And if it were to be VDL, you take the distance to be equal. So bending moment when x equals to 20 meter, you will have at this edge here, right? That is 0, 10, 20. At this 20 meter will also be, I told you it is 0, right? So you can take distance as well. You find out is equal, is the same thing. So when you find my bending moment here, that'll be the total distance is covering is 5 times 20, right? 5 times 20. This distance is covering, this force is covering the total distance, that is 20. Now also, if I cut it here, this 10 kilonewton is covering the distance here, which is what? 10. That'll be 5 times 20. Don't forget this is clockwise and anti-clockwise. That'll be 5 times 20 is covering total distance. And this one too will act like this. And that'll be minus 10 times, what is distance? 10. We find out that is 100 minus 100, that because what? 0 kilonewton meter. Okay, so now I come again. I said here we have the diagram like this. We have the force 10 kilonewton, we have the distance 20 meter. So in this concept, you find out A and B. So here, the bending moment here is 5, the force is here is 5. So if I want to pick the bending moment here is 0, here is 0 as well. And if I want to pick it here, when x goes, that will be 5 times what? Distance is covered, which is what? 55 times 10. So if I want to draw the bending moment diagram here, let's go to diagram in full now. The bending moment diagram will look like this. The bending moment diagram will look like, you draw your straight line as well, like this, yeah, at point A, point B. At point A, point B. So at point A, the diagram, the point is 0, the bending moment is 0, right? 0 kilonewton. And when it gets to point x equals to 5, so here is the 10 meter, okay? 10 meter, and here is 20. 10, 20 meter. So when it was x equals to 5 meter, that is when it was 5, or let's say x equals to 10 meter, the distance was 50, so you count 50. So this can be 50. So when it was 0, it was 0. And when it was x equals 10 meter, that is 50 kilonewton. So 50. So from here to here is 50 kilonewton meter. And it goes straight. And it comes back to 0. So note that only simply support diagram are always straight, very slant and straight. So I can combine this diagram with this guy here, and I'm gonna have something like this. So see, like I said earlier, they're gonna draw the bending moment. I have something there. So this is shear force, and the bending moment diagram, B.M.D, S.F.D, P.L.D. P.M.D will be, you see, from here, 0.0. So this is to follow the same pattern here. So I will have it as 0, right? 50. So here is 50 kilonewton meter and comes back to 0. You can now therefore shade it like this. That is the bending moment diagram. So I can retrace the diagram, and you find out that diagram all look like this. Sorry. Yeah, correct. This is the shear force diagram. This is the shear force diagram. So you see, and you can therefore shade them like this, and but you don't do this because this is simply support. If you do that, that will be variant distribution. So this is the bending moment, points, load, and shear force diagram appropriately. Also, we have what we call sagging and hugging. When the diagram of the bending moments of a question is in form of, is in this way, or is acting as if it's a concave. You know what a concave is? A concave is a kind of diagram or a kind of wave that is somehow it's somehow big at the end. So this is sagging. It's sagging. You know, when those guys say those guys you should not sag, just like sagging. And hugging is when it's like this. Sagging, S-A-G-G-I-N-G. Hugging is when it's like this. So, and that is that about that. So one other thing I really want to pay attention to is that when talking about sagging and hugging, we have the positivity and the negativity there. So when we talk about hugging, the sagging is the positive, while this is negative. So this bending moment here, it's not positive, it's what? Negative bending moment. Okay. So that is that about that. And now come back to that example there. So now, resolving this question, you can find out, you draw diagram like and so you draw diagram again, solution. So you draw diagram like this. So having drawn it again, point A, point B. Now you have your reaction RA, reaction RB. So that is RA. We have the total distance here as 1.5 meter. The first acting, so here is 0.5 and here is 1.0. You pay your diagram very well. So after that, next thing you do is you do what to now find the point load. So as usual, you have your point load and you have the force there. So the force there we can call it P or F, is that is the load. So the point load you have here is what? That is a 15 kilonewton. Right? So that is the point load there is 15 kilonewton. Okay. Then we have the total length to be equal to 1.5 meter. So from here you can resolve first thing that your total force RA plus RB will be equal to the force, that is clockwise and clockwise. Clockwise equals anticlockwise, that will be equal to what? 15 kilonewton. Then from there you can make RA, so you can say RA equals to, you can say RA equals to 15 minus RB, equation 1. So therefore you can take moment to get your RB. Taking moment about or at point about point or at point A. So I'll take moment about point A or at point A. All force will direct back to point A, and that will be this, and this will also come here. That force 15 will come here. So at this point I'm going to have my RB clockwise equals anticlockwise. RB will be covering 1.5 distance, so that will be 1.5 RB equal to 15 times 0.5. So 15 is covering 0.5. That will be 15 kilonewton times 0.5. So therefore I can say, or RB equal to, that is, or means when you resolve this, that will not be 15 times 0.5 then divided by 1.5. So but something also is that 15 times 0.5 and then divided by 1.5, simple calculation, you can do well to 5 kilonewton. Then you can substitute your equation 1 to get RA. So RA will now be equals to 15 minus RB, and that is also equals to, or RA equal to 15 minus 5, and that will be 10 kilonewton. So therefore RA equals to 10 kilonewton and RB equal to 5 kilonewton. So that is that about that. Now next thing is to determine the shear force. So if you want to determine the shear force, right, shear force, that is for shear force, the shear force at point when x equal to A, or you can say when x equal to A, yeah, that will be what you have there. The force you have in there is what? RA is now 10, right, kilonewton. Then RB is what? 5 kilonewton. So that will be shear force will be equal to, at point A will be equal to 10 kilonewton, because it's equal to what? RA. Also shear force at x equal to 0.5 to here, from here to here, that will be 0.5 meter. That will be equal to, the shear force at this point will now be equal to this one, because it's like you cut this into two. So if I cut this into two, that will be 10 minus clockwise minus anticlockwise. So that will be 10 kilonewton plus 10 rather, plus 10 kilonewton minus what? 15, and that equals to minus 5 kilonewton. So that is that about that. Now if I would also get the shear force at the shear force as well at x equal to my B. When x equal to B, the shear force will be equal to, or that will be equal to that force there. So, and you can also say that will be equal to, if I cut it here, that will be 10 minus 15. plus 5. It will still give you 0. Okay, that will be 10 minus 15 plus 5. That will be equal to what? 0 kilonewton. Okay, or if you want to make it, if the shear force want to be 5, you should remember when you want to half it, that will be equal to the shear force there. So that's the shear force here. Okay, so and if you want to draw the bending, let's find the bending moment as well. You want to find the bending moment as well. The bending moment as well will now be equal to the bending moment at x equal to a will be equal to, so as you take bending moment at a is always what? 0 kilonewton meter, don't forget. And bending moment at x equal to 0.5 meter, that will be equal to, at this point you take clockwise and clockwise, right? So for clockwise, RA is covering 0.5, right? That will be 10 times 0.5 clockwise minus anticlockwise, minus 15 times, and this is 0, right? So that will be 10 times 0.5. When you go to 15 is times 0, so it does not have any distance. That is just there, and that will be equals to what? That will be equals to 5 kilonewton meter. Okay, so not that 15 here does not have a distance. The 15 here has a distance, but it is 0. So bending moments at x equal to a final, that is b, will now be equal to, this is subscript. Okay, it should be written like this appropriately. See the way I wrote it? This is the appropriate sound. So bending moment at x equal to b will give you, what's that? 0. You can also calculate by taking 10 times 1.5 minus 15 times 1.0. So let's see that will be 10 times 1.5 minus what? 15 times 1.0. So you see finally you see 15 minus 15, that will be equal to what? 0 kilonewton meter. So from this diagram and from this solution, you can now form a you can now tabulate your diagram. You can tabulate the readings. You can tabulate it in a more specified or specific way, and you can have it as something like this. So from here we have all our answers. Okay, so over here, when you tabulate this, you have it as your sign, that is your symbol, maybe 1 2 3. Next thing you find out is that we have here as your reaction. Okay, x1 you have it this reaction here. For number 1 you can say for reaction A, or for symbol you can have next thing as reaction, bending moment, shear force. Okay, so if I have my reaction here, I can have next thing you can have here, you can have your shear force, you can have your bending moment. So at this point here, you can eventually plot your table and tabulate it. Point 1, that is number 1, number 2, number 3. So, and these are just the parameters you have. So at point A first, next thing is at point 0.5. So at point 0.5 you can name it C, because this is A, B, C. So I can say or C, that is provided I use it here, or 0.5. And I can also here use it as what? 5. That is at 1.5 meter. So it's best advisable. It's best if you put throughout, you use letter throughout or decimal. So if I want to use letter throughout, I will come back here that at 0.5 it will now be at point C. Okay, provided I've changed here to point C. You get what I'm saying? So I change it to point C. Here is point C, at point C, and also here to what? At point what? C. So at point C and at point B. So at point C I'll have it as you can arrange this if you want. At point A, my reaction is 10 kilonewton. At point C is what? My reaction is not 10, it's still what? Oh sorry, at point A our reaction is 10. Yeah, that is plus. For reaction is 10 rather. And at point B our reaction is 5, but at point C our reaction there is nothing, and that is equivalent to 0. And at point C our reaction there is also, this guy is still 10 from here, so our reaction here is 0, and for point B our reaction is what? 5. So at point C is nothing for reaction. Then the shear force at point A is plus 10. Point C we have it as minus 5 kilonewton. Point B we have it as 0 kilonewton. Then also bending moment at point A is 0 kilonewton meter. At C is 5 kilonewton meter, and this is 0 kilonewton. This is positive. Okay, now that is how to tabulate the table. So you cannot plot your graph. So plotting your graph, don't forget, you plot it, you draw it beneath the question. Okay, you plot it beneath the question. So you want to plot the graph. First of all, let's say this is a graph table. Then you plot a straight line. After plot a straight line, next thing you do is you pick a point. You first of all draw the point load diagram. So the point load diagram constant we have here is, first we have the distance here, that is the force, which is what? 15 kilonewton. We have the distance to be what? 1 meter. So you can section this part like this. Now sectioning this part here, you can have it as point A, point B. Section this part as well. So next thing, this is the point load diagram. Make sure you say the name there. The next one is the shear force diagram. Now the shear force diagram, you need to understand the distance. The shear force diagram will now be you picking a point there, right? So let's say this is our centrality. The center line there we have, that is the centrality rather. At this point 0 here, you're going to plot the graph. So remember that your reaction is 10, right? Everything is 10. So your shear force is 10 kilonewton. You pick 10. This is 0. This is 0. 0, 10. Plus 10. Plus 10. The next thing, it is constant, right? Remember, it is constant. Constant. So from point A to point C is what? 5. So I have point C here, 5. So that is point C rather. So I have it as minus 5. So when it is constant here, I have it as minus 5. So let's say minus 5 will be half here. This is minus 10. Somewhere will be minus 10 here, right? And this is minus 5. So it will be nearly half, like this. Okay, minus 5. That is if I plot my graph here. And the next thing is 0. So it is constant here. Constant. That is on a straight line. Straight line. Then it gets back to what? 0. So I have it as 0. So you can say I come again. From here you can find out that it will be, from here we have it as shear force is plus 10. Next thing, minus 5. It's constant rather. From 10 constant and minus 5, you come to minus 5 here. Adding it to minus 10 to minus 10. Okay. Then from here it's constant as well, and you find as what? 0, 0. So the bending moment diagram will now be as well. You have this. So the diagram for this guy will not really be this. So the bending moment diagram will be at point A. You have at point A you have 0, 0. I told you that the bending moment diagram for ordinary simple supported is always straight. If it were to be UDL, that is uniform distribution load or distributed load rather, you have your shear force to be something like this, and you have the bending moment to be something, it can so much be curved like this, to be curved, okay, curved like this. That is for UDL. Now add it were to be VDL, that is varying distributed load, we have it as if it to be VDL, you will have the shear for the bending moment diagram to be the shear force diagram rather will be something like this. It will somehow be smaller and big, you see. So but that is for UDL. Now for VDL, it won't be straight. It will not be something like this. You see how it curves, okay, like that. Then the bending moment diagram can now be like this. It somehow adjust here and be longer here. You see, it is somehow adjust here, then to be longer. Okay, then the diagram cannot be like this, and that's diagram the varying distributed load diagram. Okay, so this is if you want to plot the bending moment, that will be 0 plus 5. That is plus 5 is somewhere here, plus 5. Then just pick it straight because it is what point load PL, then 0 back. So you cannot do it to do this, but don't shade this because it's just ordinary what point load. Okay, and in this context I told you about sagging and organ. So this is what sagging minus VA. Okay, so that is that, and that is that about that. So you can also try this question. Try this 20 kilonewton, and from here is 8 meter. Point A, here is 2 meter. Point B. So draw the shear force diagram, bending moment diagram. Okay, draw for this. All right, so let's consider next example. All right, so here's an example, another example 2. After this example, you take a break. Okay, say 10 minutes. If you're exhausted, you come back. Okay, now this example is very straightforward and it's very, very simple. Okay, the question says that a beam 4 meter long is simply supported at its end. Very simple. A beam 4 meter long, right? So this beam is 4 meter long. Solution is 4 meter long. Simply supported at its end and carries concentrated load. So at its end means it is supported like this, that is, let's say point A and point B at its end, and carries concentrated load at point load, like I said, carries concentrated load of 20 kilonewton and 50 kilonewton at distances of 1 meter from end A. So from end A 1 meter, this load has 20 kilonewton. So 20 kilonewtons here, and 2 meter from B, that is 50. So 2 meter from B, that is B, 2 meter will be here. That is half of this, right? So we're gonna have half as 2 meter, and the remaining one here will be 1 meter. So we have 2 meter from here, that is here, and that will be, if that is 2 meters, so we're gonna have here is 1 2, and we're gonna have it as 50 kilonewton. Say draw the shear force and bending moment diagram. So this is the diagram of this. So this is solution diagram. Then to solve it as usual, what do? Write out your point load, right? So point load, I'm gonna redraw the diagram again, very clear, so you can show the reactions there. RA, RB, 20, 40, 50 rather. One, 2, 4 meter. So the point load Total point load is 20 and 50. So that will be 20 plus 50. So total point load will now be equals to what? 70 kilonewton. Okay. Then your total length of the beam is what? 4 meter. So first thing is your reaction. So taking reactions from both ends, you have it as what? Clockwise equals to, that is Ra plus Rb, because what? 20 plus 50, like a, and that equals to 70, and therefore Ra will be equals to what? 70 minus Rb, equation 1. So next thing here is this: you take your moment. So take moment, regardless anywhere you take the moment, you would always be correct if you take it to take a moment. Taking moment about point A, will now be, all force will be directed back to A. This will come back to A, and this guy will come back. This guy will come back towards A. Okay. So RB clockwise, right? So RB will be covering how many distance? 4 distance. That'll be 4 RB will be equal to 20 is covering 1 meter. That'll be 20 times 1 plus 50 is covering how many? 50 is covering 1 plus 1, 2. So 50 is covering 2, right? So that'll be 50 times 2. And that'll be RB equals to 20 plus 100. That is 120 divided by 4. 120 divided by 4, you're gonna have it as what? That is 20 divided by 4. So $30 kilonewton. That is your RB. Now you can get your RA. That will equal to 70 minus RB. That is 70 minus 30. That equals to 40 kilonewton. So in this state here, we've gotten the reaction at both ends. So we can therefore get our shear force and bending moment for ordinary simply supported diagram. So for shear force, I'm going to solve both at once. Okay, so for shear force at x equal to A. So let's say is it point A, point B, point C, point D. So at x equal to point A, the shear force will be equal to what? The RA, right? And we've gotten our RA as what? 40. Our RB as what? 30. So our shear force will be equal to RA, which is what? Plus 40. Our shear force at x equals to C will be equal to, that will be 40 minus the 20, right? 40 minus 20, that will be equals to plus 20 kilonewton. Our shear force at x equal to D, that is at x equal to D, what? 40 minus 20 minus 50. 40 minus 20 minus 50, that will be 20 minus, that will be minus 30 kilonewton. Our shear force at x equal to the B, which is the last part, will be equal to the force here, right? And I told you can also be equal to 0. That is when you do 40 minus 20 minus 50, that will be minus 30. Minus 30 plus 30, that will be equal to what? 0 kilonewton. Okay. Then now, considering the bending moment at x equal to A will be equal to 0. I told earlier, right? But there's no force here. It's just 4 times 40 times 0. So the bending moment at x equal to c will be equal to 40. What if I say at c? That means if I cut this part away, that will be 40 times 1, right? 40 times 1, that will be equal to 40 kilonewton meter. The bending moment at x equal to d will be equal to, at d, if I cut here, that will be 40 is covering how many distance? It's covering what? 2 distance. That will be 40 times 2, and you see that will be minus 20 is covering 1 distance, right? 40 times 2 minus what? 20 times 1 minus 20 times 1, and that will be equal to 80 minus 20, that will be equal to 60, and don't forget it's plus 60 kilonewton meter. Now bending moment at x equal to b, at x equal to b, that will be 0. If you know, if you do it, if you find, take the moment, but bending moment to be equal to 0 as well. That will be 0 kilonewton meter. So from here we can now draw our diagram. Okay, so we've obtained our area and RB to be this, right? So you can draw the bending moment diagram, very clear and very fine. So you can do it to try it. Pause. You can pause it here and draw diagram and confirm it. Okay, so pause it, the video, PAUSE, pause. Then once you pause it, draw the diagram and continue to check it. Okay, so now continue the diagram, you find out that you have it as this. So it will look like this. Very straight. So yeah, then the point load diagram, shear force diagram, bending moments diagram. So the point load, you have the diagram. Original diagram was like this. This in your graph. You need to draw this in your graph, okay? In exam, right? Very fine. So diagram, you can see diagram is here. Let's reprint the back. So I have my 20 kilonewton. I have my 40 kilonewton. 20. I have my 40 kilonewton. Then I have my point A, that is point A, point C, point D, and point B. So, and you section it. This is section. So once you section this, the next thing you do is you start okay, yeah, next thing you do is you start drawing your shear force diagram. All right, let's go to business. Okay, so like this, you do a shear force diagram. Now from the question, the shear force diagram is, you draw centrality, that is the neutrality line, then that is at 0 for the shear force diagram. Then at point A, you have it as plus 40, so you're gonna go up 40, assuming this is what, 40. So this is 40. From 40, see, it goes straight line, right? So this is a straight line, it's constant, then it's dropped by 20. So yeah, at point C is what, 20. So this is 40 from here, 40, then it's dropped towards 20. You see the answer, not this 20, I mean this 20 here, plus 20. So it dropped half to 20. Having dropped half to 20, next thing it does was, from that 40 there, that is at point D, it drops towards minus 30. Okay, so, and one thing about this is that this 40 is constant. So from 40 it drops to 20, right? This 20 here is now constant. Okay, when it drops to 20, next thing we have is that at this point D, it drops to what, minus 30. So minus 30 will not be up to this 40. That's minus 30. It drops down like this. to this point, minus 30. The next thing it does is from this point here, you find out that this is what 0, right? So it's constant as well, and it drops to 0. Okay, so I come again, you see, from a 40, then it's constant here to what, 0.620, dropped a bit, then minus 30. As when it goes to 20, it's constant again, then minus 30. That is minus 30 here, then it's constant and drops to 0. So this point B. Now the bending moment diagram as well, draw the centrality line, that is neutrality line. Also, the next thing you do is you start as well 0 here, right? So having that 0, and at point C here as well, at point C is what, plus 40. So you're gonna have it as point C is 40. So 40 from 40 here, then at point D is 60. So that will be 6. You see, at point C is 60, so that will be like this. That is from 40 to 60. Bending moment for shear for just ordinary simply supported is not slant. Don't forget, the bending moment is always slope, is straight. Okay, it's always straight. That is slant. So it's not like you draw 40, you not draw like this. Sometimes it's always like this as well. Okay, but in this case study, it's depreciating by 20. You can see it's depreciating. You can see the load is increasing steadily. Okay, it's increasing steadily, and that is 20, 40. So it's increasing steadily. So here you can have here as 0, 40. So even another way, you can simply say from 0 to what, 40. So I have 40 here. On your graph you see the diagram very. So 40, the next thing you find out is 60. So on D is on 60. 60, you see, find out that this is here. From here to here is 40, and 60 will be like this as well. Then that will be 0 to come down straight. To come straight. Why this here will be somehow like this, then like this, slant on 60, and you can shade like this, and this is also sagging. Okay, like that. Not that they are, you can draw some, they'll be you will find out that they are also organ is the OWG ING, but this is sagging. This is sagging ING. Okay, so that is all about that. Yeah, now we move to UDL, cantilever. Okay, all right. For cantilever is hinge to the wall. So before we get to cantilever, I'll treat UDL first. Okay, so next is UDL. all right, so we're considering uniform distributed load. All right, so don't forget to do what to subscribe to the channel, and if you have anyone that want to join, you can leave them my contacts and let me know. Okay, so my name is once again Prof, nickname or you say Peculiar Tutorial. So you do what to subscribe to it and let me know. Very important. So considering UDL, if you want to consider UDL is example is uniformly distributed load. Now all UDL progress very significant, whereby you have, for example, the diagram will look like this. Example, look at the question. This is a question. If the question is UDL to be like this, then you will have the beam to be like this. Okay, you see. So This is UDL. You can see at point A, at point B. So this is R, this is A, this is B. So this will be in, you'll be given that this distance is in weight. It's always in kilo Newton per meter. Okay, this is always in kilo Newton per meter. Okay, so UDL, uniform distributed load, and for example, like this is uniform distributed load. It distributes accordingly and it varies equally. So here is length L. If you don't forget, from the previous examples, if you have, this is point load and this is in form of a rectangle. So for UDL, to calculate UDL, you would need to find and convert to point load. So you convert UDL to point load. Now to convert to point load, you would need to do it like this. So first thing is this can be written, this is weight, or you can call it the weight, which is in kilo Newton per meter. You see, it is in Newton per meter, and this length is in meter, right? So you can do it to say, let's say this is W, and this is the length. So this is W and this is the length. So you can do it to apply area. So the area will now be equal to length times breadth, right? Which is WL. Now, whenever you convert UDL to point load, the UDL will be at the center. Whenever you convert UDL to point load, it will always act at the center. That is the gravity. The center of the gravity will act at the center. So the load will redistribute from each of these points and come to the center. Then you have something like this. It will be at the center. So I come again like this. So for example, you want to solve this. The point load will now be, convert this to point load, and that will be this times the length, WL. So when you convert to length, it will be like this. When you convert to point load, rather, it will be like this. That is the reaction A, reaction B. Then this guy would come, and this will act to the center. It will automatically act to the middle. And if you remember, the total length is L. So this will be L over 2. That is the half. Okay? So this half will be L over 2. Then once it acts to the center, then you can do well to now calculate the normal point load. If you remember, the actual point load in solving any question, let's say the point load is this. Let's say 5, and this is RA, this is RB. To solve this question, so let's say here is 10. To solve this question, what you do first is you do well to take a moment. So let's say from here to here, let's say these are the center. From here to here will be 5 meter, 5 meter. So this is 50. So if you want to solve this, then from it, what you do, that will be RA plus RB equals to what? 50 Newton, right? Or let's say kilo Newton. That is and you can make RA solve the formula. That is the first part. The second part you do is you take moment, right? So you take moments. You take moments at point A, right? So all force will be directed back to point A. And that means you are going to do like this, right? RB, that will be 10 RB minus, or 10 RB equal to what? 50 times what? 5. Times 5. Or in another statement, you can simply say, this can be written again as what? 10 RB minus 50 times 5. Okay, so you have like this and can be equal to 0. Okay, so in another way, the same thing applies to this as well. So if I want to So if you want to do this as well, when you have the point load to be WL, that is length times breadth, you convert this to ordinary length. So this has now become ordinary point load, like 50 kilonewton. You see, this does not have meter, okay? So when you have the ordinary point load, then you can now furthermore, you can do well to do something like this. So from here, I have, when I just, this is now WL, is now in ordinary kilonewton. So you can now do it to do your normal multiplication. So if I once you do the point load for this, you need to do this as well. Then you take the moment, you do it to multiply it, okay? That is by the half. That will now be WL times L over 2. So you would multiply by the half, remaining half of this, okay? So then you have it as WL square over 2. Alright, I come again for simplicity and for revision. Said whenever you want to do your UDL, you have something like this, okay? So you first of all convert to point load. To convert to point load, you need to do your length times breadth. That will be W, because this is kilonewton per meter. You need to multiply by the total length. That will now be WL. Since you convert to WL, it will change to half. It will give you something like this. So you convert this UDL to ordinary point load, then it will act at the center. The gravity will act at the center. Then you can now, since the distance is L over 2, you can now complete it to multiply by the remaining half. Okay, that will be WL times L over 2. That will be WL square over 2. Now applying it to solve the question. From here, you would now make sure you're writing all these down, okay? So if you want to solve this question, first thing like usual you do is you write your this is UDL. The UDL is W. Your UDL equals to W kilonewton per meter. Then your other UDL equals to W kilonewton per meter. Your total length is equals to L in meter. So to solve, then what you do next is you start convert this. You, as usual, you take your moment, okay? Sorry, you take your reaction. That will be RA plus RB equals to what? Instead of the total, instead of the point load here, rather you have is what? WL. So you convert this to point load, okay? If you remember, if you convert to point load, it will change. It will give you something like this. It has now changed all this to be WL like this, okay? So you have it to be your RA and RB. So when you convert to point load, that is, you have ordinary in kilonewton, ordinary kilonewton. So that will be RA plus RB equal to WL. Okay, that is equation 1. Next thing you do is you now take moments. So if you convert this, the diagram for this thing here is this. This diagram is this. That is, when I convert this to point load, just like the previous question of simply support, is like this. Then you can now take your moment. But once you convert this to point load, it will always act at the center. Don't forget, it will always act at the center. So you have it as WL, always acting at the what? Center. So it will not act at the edge, it will act at the where? Center. So if you act at the center, if you don't want to take moments at point A, so let's say you want to take moment at point A here. This is also this point A. What do you do? All force will be directed to what? To A. That will now be, from here you can say your RA equals to WL minus what? RB, equation 2. So next thing you do is you take moment at point. Taking moment at point A, you can do like this. Moment at point A equal to 0. This is an appropriate synonymous way of showing you are taking moment. This subscript A equal to 0. Then if you want to take moment at point A, what you do next is you do well to redirect all the force back to point A. That would now be RB times total length, okay? RBL, right? Clockwise is equals to anticlockwise. So that will be RBL equal to what? Complete that. Your WL times what? This length it's covering here, which is what? L over 2. L over 2. So you're gonna have it as RBL equals to WL over 2. But this will be WL times L over 2. Because you're gonna have it as this, you've converted this to point load, which is WL. Then if you multiply it, you could take you take our moment, that will be RB times L over 2. Like, you know what I'm saying? But this is total L. So that will be RBL clockwise equals to anticlockwise, then equal to WL, the point load, times what? L over 2. Just like the way you take normal one. Let's say this is 5, this is 7, this is 7. That will be the first here times the total equal to what? This times the remaining half distance. So you're gonna have something like this. Now I come again, because you need to make sure you understand this. So again, you want to resolve this kind of question. What do you do? From your UDL equals to what? W kilonewton per meter. Next thing you have is your length. Your total length is what? L in meter. Then your point load, this is RB, sorry. This is B rather. Your point load will now be W times the total length, WL, that is what? In kilonewton. So now I said you want to start your RA plus RB equal to, that's you convert to point load, WL, equation what? 1. Now when you convert to point load, diagram change, okay, and it will act at the center. So you're gonna have the diagram like this. This will act to the center. It will be at the center, that is WL. And you have your normal reaction RA. You have your second reaction RB. You have its total length it's covered, which is your L in meter. So remember, when it's acts at the center, you have what? L over 2. L over 2. So you take moments. Now taking moments at point A, you can write it like this. Summation A equals to 0. Okay, so if you take moment at point A, all force will redirect itself back to A. That means this will cover the total length of what? L, and this one will cover the total length of half. That will now be equal to 0. Be RBL equal to WL times L over 2, and that will be RBL equals to WL square over 2, and that will be RB subscript B equals to WL square over 2L, and that will be RB equals to, this we cancel this, and that will be WL over 2. Okay, so therefore we say RB equals to WL over 2, equation 3. Then equation 4, this is equation 1. Equation 2 would be from here, equation 2 rather, or say this is 3. The equation 2 here you can get to remember, that is RA equals to WL minus what? RB. That is from here. You know, you change this and bring this here. So you can now substitute this guy inside here, and that will make RA equal to WL. Your RB is now WL over 2 minus WL over 2, and that will be 1 minus half. That will still give you WL over 2. Okay, it's just like saying 1 minus half. 1 minus half, that will still give you half. Okay, so that will be WL over 2. So therefore we can now say that RB is WL over 2 and RA is WL over 2. Okay, so I believe you understand that. Now let's get into practical application. So once you are through converting it to point load, your shear force remain the same, and you do some other things for bending moments. Okay, so therefore now bringing into question, let's consider this example. So this is a question. Draw the shear force diagram and bending moment diagram. Okay, let's draw the S.F.D and B.M.D of this question. This is a UDL question, uniform distributed load. Then next thing you do is you first of all write the parameters out. So you have the uniform distributed load to be 5 kilonewton per meter. Okay, you have the total length to be 3 meter. Then you have your point load. Okay, your point load will now be what? 5 times 3, and that will be 15 kilonewton per meter. So next thing you do, you understand that you convert to area. Okay, now you draw a diagram again. That is from the equation you have your RA plus RB to be equals to what? That is the 5 times 3, and that will be 15. Okay, kilonewton. So you can have it as Ra plus Rb equals to 15 kilonewton. That is equation 1. Next thing you do is you write Ra equals to 15 minus Rb, equation 2. So after this, your diagram will automatically from this point to become something like this. Let's use this place. That will be something like this. You have the diagram again. You have your Ra reaction at A, Rb reaction at B. Then you have the point load to be at the center. Once you do take the point load, that will be 15 kilonewton. Then you have your total length to be 3 meter. Then you have here to be 3 over 2 or 1.5. That is the center. 1.5. That is the half. Okay. So next thing you do is after that you do what to take your moment. Okay. So take a moment about point A. That is equal to 0. You have it as every force will direct back to point A. So that is Rb. That will be 3 Rb clockwise equals to anticlockwise. This would get here, okay? This would come to this point here. That will be 3 Rb equals to 15 times 1.5, okay? And that will also give you 3 Rb equals to your 15 times 1.5. You're gonna have your answer. So and that will be 22.5. And you can have your Rb now because it's 7.5. That is kilonewton. You divide it by 3, so you have it as 7.5. So therefore you can get your Ra as well. If you want to get your Ra, you can take moments as well and say, okay, 3 Ra equal to 15 times 1.5. You see I have the same answer. So Ra can now be 15 minus Rb, guys, from here, and that will be 15 minus 7.5, and that will be 7.5 kilonewton. So therefore Ra is equal to 7.5 kilonewton and Rb equal to 7.5 kilonewton. Okay, so that is that. Now next thing you do is after getting the Ra and Rb, you can eventually say Ra is 7.5 kilonewton and Rb is equal to what? 7.5 kilonewton. Now this is for the reaction. Next thing you find is you do for the shear force. Okay, so if you want to find for the shear force as well, the same thing you applied so far is what you're gonna apply. Okay, so if you want to apply that for the shear force as well, is this, you know, the shear force talks about the different you take the force, that is, you consider the force. So at each point you would resolve it. So see, for example, now you want to take for this. So sometimes it's best fit if you generate the formula for it. So what will I do for shear force? That will be the reaction A here. Let's say Ra and Rb. So the reaction Ra, that is about you. It is uniform distributed load. It will vary. So that is, you can say if you want to split this, you can split this to 3. That will be 1 when you have the first 1, 2, 3. That is, you will split it into 3. That is, you can split into 1, 1, 1. Okay, so that means that from here to here is 1, the next one is 2, the next one is 3. So you split it into uniform distributed lengths. Okay, but this is uniform distributed load. Okay, UDL. So what you do is at each x in point in time, you would do it to find the solution. So how do we start? That will be your Ra. You remember, you consider the force Ra at x equal to 0. Okay, that will be this force minus, let's say we want to start when it is 1 meter. You know, normal, if you want to do for your uniform, if you want to find the shear force for this, that will just be what? 7.5 minus what? 15. Okay, and that'll be minus 7.5. Okay, but for UDL, you will not just stop here, you will not just start there, rather you would start from when x equal to 0. So shear force when x equal to 0, that is when x equal to 0, you have it as just the force acting here, and that will be equal to Ra. When x equals to 0, your shear force is equal to what? Ra. Okay, so that will be shear force when x equals to 0 is equals to your Ra and that becomes to 7.5 kilo plus 7.5 kilonewton. Now, next thing you do is when it is shear force, when your x equals to 1. So it's very important you split it. So someone will say, what about if it is 20 meter? You will not have to do one by one. If it's 20 meter, you will split into, let's say, 5, 10, 15, 20 to not waste time. Or you can say 4, 5, 4, 8, 12. You can split it to varying load, but you must let it be equal. So for shear force, when x equal to 1, will now be your RA. The RA, this RA minus, when length is equals to 1, that means when from here to here, when it is 1, you will need to, it will be RA times the 1 meter, right? So you can simply say, we can now say that let's do for x. So if you want to do for x, you can use it for UDL always. So now you can bring this example. Then for RA with length x, okay, or let's say length L, and you have your WK Newton meter. You have your UDL. So RB. So if you want to do shear force, that will be, let's say, for when L is not full. Let's say when you want to split, let's say when L is example, when it is 1 for different section of L. So let me say a first section of L is x, okay? That will be RA. If you want to take the shear force at point x, shear force when x equal to x will now be equal to this RA. When we multiply the total length, it stops here. That will be RA times x minus, here you're going to have this particular portion here for this x length will now be out. So you can say this is the weight, W kilonewton per meter. This W kilonewton per meter, you will convert it again to the center. Okay, so that will be this W, you convert this guy to point load for this little one you are doing. So that will be W times the length, which is x. When you convert to point load, it will act at the center of this little one. Then, and the length of this will be x over 2, x over 2. That will now be times x over 2. So that will be equal to RA x minus WX square over 2. This is the formula for shear force for UDL. Now, don't just cram this formula, because when you have combined load like this is UDL. UDL can be represented as this on a load. Then you have something, you can have VDL, that is very distributed load like this. And you can have cantilever as well. This is no problem, but it's just a bit long and just solve it. So you need to do the uniform distributed load, and the shear force, the diagram can look like the S.F.D can look like this. From here to be very distributed like this. Then here will be straight. Here can be straight, and it will now turn like this and it's come like this. But we're gonna come to that. So I'm telling you that you don't just cram this formula, okay? We're gonna use it here as well. So I come again, okay? So let's say you have a question which is UDL. UDL is given like this load. Or let's make use of this diagram here. So let's say this is UDL, 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 UDL. So you want to solve this. What you do next is for shear force. The normal way you do for shear force is what you do. So for shear force, you will do well to for each point. So let's consider the point when x, let's say this guy is not given. So let's say the total length is L. So let's consider this little point. Let's say we want to cross section this. Let's say we want to split this into 5. 1, 2, 3, 4, 5. So let me say a point there or a length there is x. That means, and let's say this is W, provided we are not given kilonewton per meter. This weight is not just the one acting here. It represents everything. That is why this arrow represents everything of this arrow. So like at each point in time, even if you cut this, you section this out and you only have this point like this. it is still the same weight, kilonewton per meter. Okay, so now if you want to find the shear force for this particular point, now I want to bring this point out. It will be like this. So you have your UDL there, then you have RA. Now this point distance is what? X. Then you have the UDL acting on it, right? So the UDL there, we have the weight W kilonewton per meter. That is only for this point. Now you want to take the shear force. That will be the shear force at point X. That means at this point X here, when X equal to X, will now be equal to, you take the moment, right? That will be RA times X, unlike the shear force for simply support. So if you want to take the moment here, it will just simply be, you won't the shear force here will not have anything to do with this X, okay, because you are not taking the bending moment. Okay, so the shear force will only consider this point, just similar to simply support. So you don't need this X there, only for bending moment. Okay, so for that, so therefore, considering this point here, only if you want to take the bending moment. So if you want to take the shear force, you would section it out. Then now we RA minus this W kilonewton per meter. You would first of all convert to point load. Okay, that will be RA minus this weight times the length. That is the total length. So this weight here, the length we are considering here is this X. Okay, now be W times what? X. Then once you do this, it will change to point load, and the diagram will look like this. It will change, and the diagram will look like this. So it will act at the center automatically. That is WX. Then you see have your RA, and you see have the X. And here will now be, you have the X at the center. You have here as X over 2, X over 2. So that means when you take this RA minus, that is clockwise minus anticlockwise, that will be RA minus, positive minus this W. You convert to point load, that is W times X, length times breadth. Okay, length times breadth. Length times breadth rather. It will convert to point load. Then you now take the normal shear force. That is, you now multiply. That will be W times X. You know, this is X over 2 times X over 2. That will now be RA minus WX square over 2. That is shear force. So you can take this shear force for every point. Okay. That will be the shear force for every point. So now bringing it down to question UDL like this. See this example question. You to also see we have RA question here. We have total length. We have the UDL. Let's say UDL made of W kilonewton per meter. So when I find the shear force, what do you do if I come here? That will be shear force at point X. Okay, so let's say the point X, let's the total length is L. The point X at this section, let's say it's point X. So the shear force at point X will now be, because shear force talks about force, this guy will now be this particular weight. You convert it to what? Kilonewton. That will be RA minus W times what? X. That is length times breadth. Now when you do this, you should know it will limit your answer. It will become point load, right? And it will act at the center. This will give you a particular specific value. And this is so simple that you don't need to progress and do X over 2. Why? This will, if you forward and do this, you are converting into, you are taking your moment. So in a nutshell, this is your formula for shear force for different load. Okay, because you are dealing with the force there. So you are simply converting this moment, that is this varying load, to force. Now let's solve this question, and that will shed more practical light to the solution. So at this point, my RA will be 7.5. So when X is 1, that will be RA minus 5 times that particular length. So that is times wx, and that is when it is x. So therefore I can have it as at x equal to 1, that is I'm going to have it as RA, which is plus 7.5 minus my w is 5 times what, 1, and that will be 7.5 minus 5, and that will be equals to 2 plus 2.5. Okay, so when it is shear force at x equal to 2, that will also be equal to what? This is subscript, don't forget these are subscript. That will be equals to 7.5 minus 5 times when x is what, 2, and when x is 2, that means or the formula, this formula, I hope you understand it, right? That is when you first of all convert to point load. So imagine, before you even talk about UDL, we're talking about simply supported, and you have something like this, okay? And in this question, if you have to find the shear force for simply support, what do you do? That would just be the RA, that would be the RA minus the force you have there. So maybe this is 5, that is RA minus 5, okay? At the bin you have another force, let's say at the bin you have another force, so that will be RA minus 5 minus this, okay? But that means this one you are converting into point load as well, to have something like this. So you're gonna have it as 7.5 for x equals to 7.5 minus what, 5 times 2, and that will be equal to 7.5 minus 10, okay? That will be minus 2.5 kilo. These are all kilonewton. Then the shear force when x equal to 3, that will be also equal to 7.5 minus 5 times 3, that is the total length, and that will be 7.5 minus 15, that will be minus 7.5. This proves that UDL is always diagonal slant. That is the shear force, okay? Now you have the bending moment. If you remember, you find your RA to be plus 7.5, right? RB is also what, plus 7.5. Now the bending moments as well, let's prove that. Bending moment at x equal to x. So let's bring the diagram here. Let's say this is UDL to know it's time, and you have your UDL. You have your RA, you have your RB. The same way you take for your RA and RB. So we have the weight here, that is the load, rather varying load, kilonewton per meter rather. So to take the bend, if you know you want to take the bending moment, let's say we want to cross section this, and let's say for each point x. So let's say here the total length is L, and for just ordinary this point x, I want to bring this diagram out. So if I bring this diagram out, I'm going to have something like this, okay? The same weight is the one acting here, okay? That is kilonewton per meter. First thing, I will convert this to what? Point load. So to take the moment, that will be the RA, what it's covering. RA it's covering, taking clockwise and anti-clockwise, right? So I want to take moment about this point now, right? That is RA times x, and the weight will come back times x, okay? Times the point it's covering. So what will I do? That will be, taking moment, that will be RA times this x minus this weight is the one acting here, okay? So that will be, I'll come back to point load first. That will be minus W times the total length. Once I convert to point times the length and cross section rather, once it is converted to point load by this, that is length times breadth area, the diagram will change to be this, and it will always act at the center. My R will still remain, my x remain, but you know when it's remain at center, here will now be x over 2 and x over 2. So that will now be RA times this, then my W, I've converted to point, that will now be WX. So that will be RA times x minus WX times what? The remaining half length, minus WX times x over 2. Okay, so therefore that will be RAX minus WX square over 2. What do I do? What I did as well is that you will first of all convert to point load. So that is area, length times breadth. That is WX. When you convert this to point load, it will always act, the gravity will always act at the center. Then that is, you have your x over 2, x over 2. That means you are splitting this into 2. X over 2, x over 2. This occurs for each point. And you have your answer, you have your formula as this. So now bringing it to this question here, if I want to take my bending moment at this point when it is RA, 0.0 here, okay, so I'm going to have it as my RA, that is bending moment as when x equal to let's say 0. That will be bending moment when x equals 0 is always 0, because the formula you always have it as RA, that is the force, okay. So, and you know the formula states RA x minus WX square over, don't just cram this formula, okay, but it's advisable you also know it. So you guys using the formula, you have it as RA, that is this, the moment you are taking is x equals to 0, that will be 7.5 times 0 minus the weight. So at this point 0, that means you are cutting, you are leaving here, that will be 5, the 5 acting here, 5 times 0. 5 times 0 target center, and everything will just be 0, okay. So at always the beginning, I told you that your bending moment is always 0 at the beginning. So when x equal to 0, you have the answer as what? 0 kilonewton. Kilonewton meter. Now bending moment when x equal to 1, yeah, here it will be what? When x equals to 1, that will be RA times 1, right? That will be 7.5. Take moments like this, that will be 7.5 times 1 minus, you know, you're talking about when x equals to 1, that will be 7.5 times 1 minus, that is clockwise minus anticlockwise, 7.5 minus times 1 minus 5 times the length of this short one you are cross-sectioning. That is, this 5 you see the one acting here, it is distributed, okay. So that will be minus 5 times 1, 5 times 1 times multiplied by the half, because it will act at the center, okay, multiplied by the half, that will be half of this 1 is what? 1 over 2, multiplied by 1 over 2, okay, or you say 0.5, okay. So that will be 7.5 minus 5 over 2, and that will be 2.5, and you have your answer as 5 plus 5.0 kilonewton meter. So bending moment when x equal to 2 will now be equal to as well. Can you give that a try? So that will also be 7.5 times 2 minus 5 times the length you are taking, that is cross-sectioning when it is 2, that is when total length is what? 2. When total length you are considering is 2, 5 times 2 times the half of that 2. Half of 2, that is 2 over 2, right? And that will be 1. So that, because it is acting at the center, that will be 7.5 times, that is 15 minus 10 times 1, that is 10, and you have it as what? Plus 5. Okay, so like this, then when bending moment when x equal to 3, that is maximum. This can also be written as dm over dx, okay, that is when, and it's always equal to 0 for sure, because at the edge you always have the answer as 0. So let's confirm that at x, that will be 7.5 times 3, right, minus times 3 minus 5 times the total length, that is for the 3 we are considering, 5 times 3 multiplied by 3 over 2, that is 1.5, and you have this as 22.5 minus this is 15, and you have this as 20.5 because this is 1.5, yeah, and you have it as 22.5, and you can have your answer as 0 kilonewton meter, okay. And also from this you can now plot your table, okay, and you can plot your graph, just very simple. So you find out that from here, let me clean, I gotta clean this very well, okay, and all right, let's quickly depict the table here. Let's formulate the table first here. So our reaction as usual, you have your table from, you have your symbol, which is your 1 2 3 1 2 3 or 4, 0 1 2 3 0 1 2 3 you have your for shear force, that is for reaction, for shear force, for bending moments, for your numbering. So for reaction, when it is 0, you have found out that it is just 7.5. At 1, at this they correspond, and you see it at the last part as what, 7.5. That is kilonewton. That is the reaction. This is kilonewton as well. Why this one is kilonewton meter. So, and this out, the out dash dash, and shear force at 0 we find out is what, 7.5. That is plus 7.5 kilonewton. When x equal to 1, you have it as plus 2.5 plus 2.5 kilonewton, minus 2.5 minus 2.5, and you have it as minus 7.5. Bending moment when it's 0, you have it as 0. Sure, you know here is what, 0, and at the middle when x1 is 5.0, that is plus 5.0. Then here you have it as what, plus 5.0. Okay, I decided to leave it in 1 decimal point throughout. Don't write 0.00, so 5.0. So therefore we can plot a table. Okay, so we can plot a table, and we can plot a graph rather. So you plot the table already, you can plot the graph. So plotting the graph looks like this. You plot your normal graph. You have a graph there, something like this. Then you have your diagram first. So the diagram looks like this. So you section it like that. Then you have your UDO. Draw your graph variance on the graph table. Your UDO. You have the length 3. You have each point. This is your UDL. Shear force diagram will now be at the center, centrality or neutrality. So at this point here, when I have shear force at x equal to 0, so you got to shift all these points. So you got to do the points. Okay, that is 1, 2, see, 1, 0, 1, 2, 3. Okay, so when it's 0, you have it as 7.5. So 7.5. When it's 1, it is 2.5. It reduces. So let's see this 2.5, 5.0, 7.5. So 7.5 is 2.5 at 1. So 1 is 2.5 here. Then at 2, it is what? Minus 2.5. So this is minus 2.5, 5, and 7. So minus 2.5 is here. It will also do well to, it will always be at the center. Okay, so that is at the center here. It will pass through the center here, and we're gonna have it as on 2 to minus 2.5. Okay, minus 2.5. Then on 3 is minus 7.5. Okay, so 7.5 plus 2.5, 2 minus 2.5, and also on 3 minus 7.5. You see, it will be at the edge. So I told you that it will always be straight. Oh, that's typographical error. Okay, it will always be straight. So the diagram will look like this. Okay, and it will be at the center. Okay, and this is a typographical error or rightographical. Should I say rightographical error? Okay, and just like that. That is. So the bending moment as well, B.M.D, will now be at 0. That is 0. So this is the neutrality point. At 0, you have 0, and at 1 you have it as 5. So it is 2.5, 5, and 7.5, 2.5, 5, 7.5. So 5 at 1. You section this guy downward as usual to get your line and to get your thin line dash. Okay, to get the point, thin line dash. Okay, so at 0, 0 here, at 1 is 5.0. So 1, this is 2.5, 5.0. At 2 is 5.0, and at 3 is 0. So one thing as well about B.M.D as well is you have this as 5.0. So you can decide to draw it something. You can decide to draw it like this. Draw at the top here, and also that's 5. It would be curve. Okay, it will be curve. It will be like this. Okay, and that is positive. Okay, so you can have it as positive, and this is it. So you can shade it, and so that is that for UDL. Okay, now we're considering VDL, very distributed load. Okay, this is VDL, very distributed load. Now VDL is very distributed load and is given as this. Okay, one thing remember for UDL is that for UDL it is uniform distributed load. When you find the point load, it comes to the center. And another nutshell recap for UDL is that you will find your half, that is length times breadth rather. Okay, and that is W, and your L, that will be WL, and it will add to the center. So if you want to take the moment, that will be WL square over 2. But in this very distributed load, it's not like that. But same principle applies. First thing is that when you turn it to point load, when you turn varying distributed load to point load, it would always act at the 2/3 of this smaller part and 1/3 for this bigger part. I come again. It's very important. When you turn or change this to point load, it will always act to at 2.2/3 rather 2/3 of this length. So 2/3 of this place, if you are taking this like this, and 1/3 of this bigger part. Okay, so this is where I mean. Now for this guy, let's say this length here is L. Here, first thing you do is you cross section. Okay, if you want to take taking reaction, you have your RA plus RB equal to the half base times area of this. So the point load for this VDL will now be, if you want to cross section this thing, you have this diagram like this. Imagine I'm partitioning like this. You first of all have this diagram like this. This is W, this is, let's say here is Y, let's say here is X for smaller part, and let's say the whole length is L. Here is X. Okay, so and this is W for the bigger part. So we can therefore say that this can also give us Y, that is of same proportion, Y over X equals to W over L. So you can say Y equals to WX over L. This is in case you want to section it. Okay, and also you can remember that this is like a triangle, so the area will be half base times height. So to change it to point load will now be half base times height, and the base here, that will now also be half. What is the base? The base is, in this question, if it's for sectioning, the base will be what? For the cross sectioning, you have your base as this, right? And you have your height as what? W. And if it's for this small one, you can have your base as what? X, and you have your height as. Okay, so now to consider this, just have in mind that we have Y equals to WX over L. So now we say that, and that will be RA plus RB equal to, convert this to point load, that will be half base times height, and that will be half WL, or you can say WL over 2. So this is RA plus RB equals to WL over 2. So whenever you want to solve this question, I will advise you that you always take your moment at point B. You can take your moment at point A, but don't forget you make use of this part as the what 2/3, and this part as what 1/3. Okay, don't forget that at all. It's very important. So if I will take my moment about point B for this concept, you won't take your moment at point B. You can take your moment at point A anyway, but don't forget the 2/3 and 1/3 part. So I want to take my moment at, let's say, point B here. I'm going to have my array with the direct here, right? So therefore, well, from here we can say that we can say RB is equals to WL over 2 minus RA. Okay, and this is equation 2, equation 1. So, and from this concept you can therefore find and convert point B. So if I want to take my moment about point B to get RA, I'm going to have diagram like this, and I'll have my RA, I'll have my RB, I'll have the VDL, I have the W, I'll have the L. Okay, so now taking moment at point B, moment about point B equals to 0, that will be, all force will be directed back to B. Okay, now if I'm taking it here, I told you that if you are considering to this point, this bigger point to be what 1/3 of it. So therefore I can have it as RAL, that is force times what distance, RAL, the total length is covering, right, equal to, that is clockwise equal to anti-clockwise, RAL equal to the turning this on to point will give you what, half base. That will be half base. What is the base? The base is what? L times height. This is the first part. Now when this is here, the next thing you now do is multiply by, it will give you, it will change this will change, just like the UDL. It will change, the diagram will now change to be like this. It will change like this, but it will act at them, because you are taking like this is 1/3, this is 2/3, it will act at the what, 1/3. The center of gravity will act at the 1/3, and that will be 1/3 of this length. Okay, that will be 1/3 of L. This part is 2/3 of the length, and here is 1/3 of the length. Okay, so because I'm taking it, we act as what, 1/3 of the length times the 1/3 of the length. So we can say 1/3 of the length. I come again, this will be RA lies times L. I take a moment about it. Then what you do for this guy is that this guy will be half base times height, half base times height times this will act at the 1/3 of the length. So you multiply it, because you will take the moment like this. Okay, so here, and that will be RAL equals to WL square over 6. So I'm gonna have RA equals to WL over 6, because L will come here to cancel this. Okay, but the Bible said by L to cancel, and as S over L to cancel, and I have my answer as WL. So that is, I have RA equals to WL over 6. So this, if I want to substitute inside to get my RB, so I can say therefore RB equals to WL over 2 minus WL over 6. So I can decide to find the LCM, and RB will now be equals to, if I find the LCM, I have 6, 2 here 3 WL minus WL. So I'm going to have it as what, 2 WL over 6, 2 here 3, and I'm going to have it as RB equals to WL over 3. So in a nutshell, we found out that our RA is what, WL over 6, and our RB is what, WL over 3. Very important. Okay, so having noted that, then therefore we know that our RA is WL over 6. Cramp like that is always applicable for all video. Okay, so we can say that our RA we're gonna write that as well. Our RA is always WL over 6 and our RB is WL over 3. Okay, so from that we can also say that you find the shear force here in this context. So finding the shear force here, 2/3 of the length, 1/3 of the length. Finding the shear force here, since our RA here, so I can redraw this diagram to give me something like this. You can just put the arrow there, just redraw it, put the arrow there, redraw it, put the arrow there, and you have here as RB, that is WL over 6, and this is what WL over 3. So in this context, what you do next is that you do well to make sure you're going to find the shear force. So I would like to go with bending moment first before I talk about the shear force, so you can really get it. Now, for considering the bending moment as well, see something. So let's consider the shear force then. So for shear force talks about the force. Okay, so shear force at any section, that means a section. So if I cut it here, I'm gonna have diagram like this, like the one I did the first time. Okay, that's our partition. So let's say here is X, here is L, and here is W is Y. So I'm gonna have my answer as Y equals to WX over L. Okay, so knowing that our Y equals to WX over L, that is at this point you have one WX at this point here, at any section it's a WX over L. So now we have our small x for each. So for any section, YF for section of shear force is A of X will be equal to, don't forget your RA, right? That'll be your RA, and that is your WL over 6, right? So that'll be RA minus the point you are partitioning or you are sectioning. So if I want to section this place, what would that be? That will be the point, the breadth I will have there will not be here, will not be W. At any section, I will have it as what? WX over. That will be, and I need to convert this to point load. That will be WX over L multiplied. That is, it will be half base times height. Okay, so that's, I want to convert to, that will be RA minus half base times height. What is my base? At any point, my base is what? X. Half base times height. My height is now WX over L. So I'm going to have it as RA minus WX square over what? Over 2L. So you see, and that is, I can now have my shear force at any point to now be equals to RA, and my RA is also WL minus, that is WL over 6 minus what? WX square over this is WX square over 2L rather, over 2L. So you see, this is the shear force. You can cram it, you can apply it for video. Okay, very simple. You can just note them down. I said combined load. So now you can apply the shear force at any point. Okay, so you want to find the bending moment as well. So the bending moment as well, don't forget, you want to find the shear force at this point is what? WL over 3, and at this point is WL over 6. You don't need to, you can apply this, you see, have 0 as well. So now for the bending moment at any cross section, because it won't be logical, you are now solving each step by step and applying the same rule. It's very better you just apply the formula and just be fast about it. So the bending moment at each section can also be, I'm taking moment about points, let's say point B. What do you have as well is this, that at any section, just take your moments around this will come here, right, and to cover 1/3. Okay, so that will be RA, that because to RA times the length it covers. So let's say at any section at any section, that will be RA times the length it covered. Let's say X, because X is short. RAX, right? Minus, that is clockwise minus what? Anti-clockwise. So clockwise minus anti-clockwise. That will be RAX minus, at any section we know it as WX over L. So that is, and we know that that is here for the height. And you remember, if you want to convert to this, what? Half base times height. So that will be RAX minus clockwise, not half base. What is the base? X. Half base times height. What is the height? WX over L. This is converting to point load. Then if you convert to point load, don't forget, if you are taking clockwise to this higher part, it will always cover to what? 1/3. It will always cover the 2/3, but you are going to make use of the what? 1/3, because you are taking it like this. You are taking the moment like this. Okay? Adding is like that with 2/3. So you are taking a line with covering what? 1/3 of that length. And that will be multiplied by what? 1/3 of the length will now be 1/3 of what? The length here is X. And you can have it as RAX minus what? This is WX cube over 6L. So here will be the bending moment at any section is equal to RAX minus WX cube over 6L. You can also cram that and jot it down. Okay, very important you note it down. And you can also make use of it over 6L. That is that. So, and you can remember that your RAX is also what? WS. So you can simply adjust it. Don't forget this RAX. Okay, so your RA is WL. That will be WL, and there will be X WL over 6. Okay, so you can have it like this. So that is minus. That is WLX minus WX cube over 6. Okay, so you can just these formulas down. Okay, and you can make use of them, and we're gonna make use of them very fine now. Okay, so let's consider this example. So considering this example, you have to draw the shear force, S.F.D and the B.M.D, shear force diagram and bending moment diagram. So in solving the solution, after writing your solution, let's say solution, next thing you do is sharp, you just do what to write out. Your VDL is 2 kN per meter. Your total length is what? 3 meters. So to convert to point load, that will be equal to half base times height. And half base, the base is times 3 times 2. That will be cancel. That will be 3 kN. Okay. Now you kind of find your reaction. RA plus RB equal to what? The point load, which is 3 kilo, equation 1. So next thing you do will now be RA, taking moment about points, or you can say RB equals to 3 minus what? RA, equation 2. So taking moments about point B, that is for this video particular. So what you do next, you are taking moment about point B, is all force will be directed back to B. So you can draw a diagram and you put your arrow there. Okay, let's do something like this. Put the arrow there, DL, and that will be 2 kN per meter, maybe 3 meter, RB. So the next thing you do is you do to make sure you take the moment. So if I take a moment about point B, what you do next is that will be RA. So you can make use of the formula not to waste time. If you remember, the formula in taking moments at any section is equal to what? Or your moment taking the any section is what? WLX over 6 minus what? WX cube over 6L. So you can apply it, and that is at this point. Okay, at taking moment about point B, don't forget at this bigger point you can make use of this. Already diagram is like this. So and you can apply it, and you can have your moment. So this one will be clockwise. The clockwise is this equal to anti-clockwise. That will be equal to 0. So that will now be this one equal to this. Okay, You can now say that Rx over 6 equal to Wx cube over 6L. Okay, so if what you're looking for is you are trying to get your RA. So in a nutshell, after you've done this equation here, you can just simply say that RA is what? Remember, RA is WL over 6. Okay, so not to waste time, if you continue this, you can just simply portray or simply put it to not waste time that from here, like after getting here, you can decide to put formula that RA equals to WL over 6, or you can just take your moment like I did now. So we're going to take a moment about point B. What is it? That is RA. That will be RA times 3. That will be 3RA. Total equals to clockwise equals to anticlockwise. And what is anticlockwise? The first combine to 100. That will be half base. The base is 3 times height. Then when it's turned to 100, to cover 1/3 of this, so times 1/3 of the length, that is 1 over 3 of the total length is what? 3. So that will be RA, 3RA equals to, this will cancel, it will be left with you'll be left with 3. Okay, so that you can have it as 3 over 3. Then you have your RA equals to 3 over 3, and R equals to 1 kilo Newton. So therefore RA equals to 1 kilo Newton, and RB can be equal to 2 kilo, that is 3 minus 1. If you use the formula, you know RA is WL over 6. See the way it is, WL over 6. If your RA is WL over 6, what is W? 2. That is 2 times L is 6 over 6. Okay, then that will be, guys, if your RA is WL, we are using the formula, and you have, so, and oh sorry, remember your L is 3, so you have it as WL, L is 3 rather, over 6, so you can have it as 6 over 6, and that will be 1. So just make use of the formula, but you can't just make use of the formula like that. So to prove this, so I come again, what do? You carry the parameter outside, you write your RE plus RB equals to 3 equals to, you find the point load. Point load is, you convert it to using your area, and be half base times that will be half base. What is the base? 3 times height. You have your point load, then you write RB equals to 3 minus RE. You take the moment about point B using 1/3 of the length or 2/3 of the length. Okay, so what you do next is you do the diagram, then you take your moments about point B. That will be 3RA equals to clockwise equals to anti-clockwise. 3RA equal to half base. Half, area is half base of triangle. Half base times height times this, we have that 1/3 because you're taking moment the bigger parts. 1/3 of the length, simple. Then this will cancel, you have 3. Then R is where you have this. We can make use of this formula. And if you remember, your RB as well is what? Your RB given as well is also WL over 3, right? So if you use WL over 3, what is your W is what? 2. That will be 2 times 3 over 3. And that becomes what? 2. So you can find out that your RB is 2. Very cheap and very fast. You can just use that for check. Okay. And we have our answer as 1 and 2. Okay, so therefore we can find our shear force and can find your bending moment. So if you want to take your shear force and bending moment of the question, I'm going to solve it of shear force and bending moment. If you remember, very simple. Shear force at any cross section of VDL is given as what? You have it as WL of 6 minus WX square over 2L. So you can just apply it at any point when X equal to, let's say when X equal to 0, your shear force is also equivalent to RA, and that will be WL over 6, which is equal to 1. So your shear force at X equals to 0 equals to 1 kilo Newton. When X equals to 1, don't forget to distribute this accordingly. Okay. So when X equals to 1, your shear force will be equal to, apply the formula, when X equals to 1, your total length is the reason why it is when X is 0, this will be 0 really. So when X equal to 1, what do you have? That will be this is equal to 1 already. That will be 1 minus, this is w is 2, that will be 2 times your x is 1, 1 square is 1 all over your 2 times l is what, 3, that is total length. So this we cancel this, and that will be 1 minus 1 over 3, that will be 2 over 3. Okay, and that is that for when x equals to 2. So when x, shear force when x equals to 3, you will have it as using the formula W over 6. Your W is 2, that will be 1 as well, equals to 1 minus wx squared. So x equals to 2, that will be W is what, 2 times 2 square over 2 times 3. From here this can cancel this, that will be 1 minus, this is 4 over 3, 4 over 3, and also you can have your answer, that is 1 minus 4 over 3, and also have it, this can also give you 1 number 1 over 3, and also you can have your, that is when x equal to 2 rather, sorry, when x equal to 2, and also when x equal to 3 is the maximum point, you can have your shear force as 1 minus, this one already, w is what, 2 times your x is 3 square over 2 times 3. This guy can cancel, this guy can cancel. 1 minus 3, that is minus what, minus 2. So one thing is this, that for VDL you must make sure that you are consistent with distribution of the load. Okay, if you are consistent with the distribution of the load, you have your answer. Okay, so most times not usually does not really have the answers to be 0, but everything with like that. So, and as if you remember your VDL, like value for RB is 2, but because it is acting negative and you have it as minus 2, you can cross check that as well, but it's better you make use of the formula because it is distributing. So at this point, now you've gotten your shear force, and we can tabulate our formula, our answers as this. So you can also find your bending moment once. Bending moment at its cross section, if you remember, is the formula for bending moment can also be WX over 6 minus WX cube over what, 6L. Okay, so when x equal to 0, you have your bending moment as, and this is 0, everything is 0 because it's x is 0. So when x equals to 1, you have a bend formula, your answer will give you as this is 1. So formula that will be 1 times 1 already, and that is 1 minus wx cube over 6l. You're gonna have this as 2. That will be 2 times your x cube, that is 2 times your x cube is considering that is total length when x is 3, that is 2 times 27 over 6 times 3, that is 18, and that is 2 year 9 year 1 9 year 3, that will be minus 2 kilonewton meter. So when x equal to 2 as well, you can have your answer as I got this as well. So you can have your answer as when x equals to, that will be 1, that is when x equals to, that will be 1 using this formula. Here is 1 already, 1 times 2, that will be 2 minus, when x is 2, yeah, you have your w as 2 raised by 3, that is 8. Okay, and that will be 2 8, and w, this is 2 raised by 3, 8 times 2, that is 16. That will be 16. 2 minus 16 divided by 6 times 3, that will be 18. Okay, you can have here as 2 can go here. In each of those, you're gonna have your answer as, so you're gonna have your answer as 1.1 kilonewton per meter, kilonewton meter rather, not per meter, meter and meter. Oh, sorry. So also you want to solve for this as well. When x is 3, you make use of the formula, and that will be 3, because you're gonna have the answer as this is 1 times 3, so you have it as 3 minus, and you're gonna have the answer 3 minus your w is what, 2, and 3 raised by 3 is 27. Okay, so and then we're gonna have your answer as sorry, this will be when x is 3 because the value there. So this is when x is 3, you can remember in the formula this should be 1 minus, so here should be 3. So changing number, we're gonna have here at 3, it should be 1, so you can make use of 1 here. So when x is 3, and this is 1 times 3 minus w is 2 when it's 3, that'll be 3 is power 3. Okay, yes, for minimum that'll be 27. Okay, and 27 6 times total length, 6 times our length 3 is 18. So here 9 here 3, 9 here 2 here 1, 2 here 9, 9 here 1, 9 here 3. So you have it as 3 minus 3, you're gonna have your answer as 0. Okay, so we're gonna do it for, let's do it for the first one, that's obviously for 3. So when we do it for the first one, you're gonna have your answer as, when x is 1, so what that be, this is 1 times 1, that'll be 1 minus, and also when you get for this, that'll be 2 times, when this is 1, that'll be 2 times 1, right? That is 2. 1 cube is 1, 2 times 1, 2, over 6 times 3, 18, that'll be 2 over 18, and that is 1 over, 2 over 18 is 1 over 9. And 1 minus 1 over 9, you have the answer as 1 minus 1 over 9 is 0.888. That'll be 0.888. So you can plot your table. Okay, very. So we find out that the shear force and the bending moment diagram, or the table form. So let's plot. I got it clean here, and we can tabulate our table. So tabulating our table here, the symbol reaction. So our reaction at the first part, remember, is 1 at the first RA, and the last one is 2, and that is B. And shear force, when it was, as you can see, this is the number, and this is 1. When you take your reading, here is 1, and you have dash, and you have 2. So if you check the shear force as well for the first one, that is when it's 0 meter, you have it as 1, 0.66 minus 0.332, and you have the bending moment as well to be 0, 0.88, 1.11, then 0. So you want to plot your graph. It looks like this. That is, you draw the VDL. This is the VDL. You draw it. Then when you draw it, you do what you section it, and that is 0. Here is 1, this is 2, and that is 3. So 0, 1, 2, 3. So therefore, now if you plot it, that is from your table, you find out that it is, the shear force is 1. So the first at point 0 is 1. Then you take 1. Then next one is 0.66. 0.66. Next one minus 0.3. Minus 0.3, and the last one is minus 2. See, here is minus 2. So you see it is curved, like this. That is VDL for you. VDL is always curved, then it goes back to point 0. Okay, so that is the diagram. Then for bending moment as well, we can see from the table, the first one we have is 0, 0.88, 1.11, 0. So that is, we have 0, 0.88. So we have 0.88 somewhere here. 0.8 is somewhere here. The next one we have is 1.11, so you need to be a bit higher. Then we have 0. So you can notice that it is also somehow curly, somehow like this. Yeah, something like this, somehow curly. Yeah, unlike VDL, unlike UDL rather. So here is neutrality, and it's supposed to shade this guy as well. That is that. So if you remember the summary reference, you can apply it. So if it were to be UDL looks like this. There is a uniform distributed load. Or let me start from point load. Point load diagram looks like this. It's just a beam. Then you have the shear force diagram to be something like this. If it has a force here, let's say it has a force here, the diagram shear force will look like this. It will drop. When it drops, it comes down to 0. dependent on how you have another force here, it's nourished. So first of all, drop from the center point. So dropped, it's come down, dropped, then something like this. Then you can have the bending moment to be somehow of an angle, more or less of a triangle, something like that. Now add bending to it. If you tell to be UDL, that is uniform distributed loop, you're gonna have it like something like this. Yeah, force can act on this as well. You know, there can be an external force. No, not on this. There can be an external force. I'm going to show that now. So you have UDL. If you're to UDL, you have the question like this. Then you're going to have the shear force diagram. It will always be diagonal, straight. And it will always be of the same distance. Okay, it's not like the video that is slant. It is always what? Straight. Slant rather. So you have diagram like that, not curly, straight. Okay, it's just straight. So and you're gonna have the bending moments. The bending moment for UDL will now be something like this. It is sequential. It is in order. You see, in order. So something like this. But if it were to be VDL, so now VDL diagram is something like this. For VDL diagram looks like this. Remember, here is 1/3 of the length, 2/3 of the length, 1/3 of the length. You have your shear force to look like this. It will always be somehow slant. It will always be somehow curly. Sometimes they are like this. You have small pointing. So they are like this. So most times they are somehow curly, very curvilinear. Once you know the diagram, you are very good to go. Okay, so you can have the bending moments. This is it. You can have the bending moment diagram, something like this. To be somehow curly, okay, like this. Well, like that. So next one we're gonna be talking about is cantilever. Cantilever is the point that it has a fixed point, and we're gonna be considering something like this. How to solve it? It's very simple. Just take the moment as well. I'll be considering combined load. Combined load are just the combination of, let's say, UDL, an angle situated at degree, let's say 45 degree, a force. Instead of just a normal question that has just some forces like this one can be situated at angle, and can have UDL on it, and just like this. Then be asked to draw it. You'll be asked to draw the shear force. So you know this is shear force will look like this. Then when you go a bit as well, that is from here. When you go a bit to go straight, cover. This one might come down a bit. Then you go straight. You know, for UDL, for VDL, it will be something like this. Go up, curvilinear. Curvilinear, and come down. So it will look something. The diagram will look like this. The diagram will look like this. Anyhow, depending on the question. So this is a shear force diagram. Then the bending moment, you can draw the bending moment as well. For UDL, the bending moment is always like this. Why this one is always like this? Why this one for the straight part here is always like a triangle? It's always like something like this, like this. Then you have this force will come down. Then you're gonna have this on a straight line as well. Then you're gonna have something like UDL is always slant. Yeah, something like this. So that is combined with the ball. That will be question solve. Okay. So also don't forget to subscribe. If you have anyone again that want to really, maybe have someone, a friend or someone in your department that wants to join, you just do it to let them reach out to me. You can send my contact to them. Okay. And also that is fun. So make sure you are good. Shall we pray? Oh Lord, thank you for this class. We see you be exalted above all things. For in Jesus' name, thank the Lord. Amen. Alright, make sure you are fine. Okay. Yeah. Good day to you all. And also look forward towards a question. questions and assignment that we submitted. So you do well to make sure you look forward to it, okay? And you do well to make sure that you submit your assignments as well. Write them in notes. Write it in your notes, then submit it. Snap it and submit. Okay. All right. The Lord is our strength.